Looks good. Okay, guys. All looking good? Feeling good? Yeah. Very good. What we're going to do first is huddle. So let's move up for huddle. Adjusting microphone. Okay. All right, I'll start talking to you while these are being passed around. What you need to do is to take one copy. This is going to be yours. So would you start there and pass them around that way? And June, you start there. Now, you can start having a look at those as they come around and listen to me at the same time. Because I want to ask you a rather strange question, first of all. And if you want more clarification, if you think you can answer it straight away, that's fine, go ahead. But if you want more clarification, you must ask me some questions, okay? You may not have heard this question before, but I'm not going to tell you the answer straight away. We'll move on and we'll discover the answer as we go. Okay, this is a question that really was put some hundreds of years ago, and people, philosophers as they were then called, not scientists, thought about it and talked about it. And that is, any solid object that you might consider, whether it be this mass or this trolley, or indeed anything, the question is, what is its natural state? What is its natural state? Now, in old days, yeah, you'll be first, just wait a minute. In old days, philosophers used to be considered a lot, or concerned a lot, about considering questions like this of natural state and the perfect shape. Anyone know what was considered to be the perfect shape?
A circle?
Close. Three-dimensional circle. Sphere, that's right, yes. So, they talked about things very philosophically. Didn't do a lot of experiments or measurements. That came quite a bit later. So, one of the questions was to be considered, what's the natural state of a body? Now, you were first, Ollie.
Oh, I thought it was an object.
Or a body or an object, that's all right, yeah.
Solid?
Or we're talking about a solid. Dana? Untouched, we're getting there. Anyone want to ask me any questions to clarify the question a bit more? What is the natural state of a body? A body is just an object, as I said, can be anything. Yourself, you're a body. Any other ideas? Anyone want to, I mean, is that question clear to you?
No.
Do you think you know what it means? Do you think you know what I'm after? Then you should ask me some questions now. What do you mean by this, or?
What do you mean by a body?
A body, good. You're a body, this is a body, I'm a body, my pen's a body. Any solid object.
So where it came from before was here?
Not where it came from. We're not concerned about where it came from. We're concerned about its natural state.
In a rock? It was in a rock once?
Well, a rock is a body, but not in a... Yeah?
Does that mean, like, what's its use?
What's it?
Its use?
No, not what's its use. I'll give you a clue now with a little demonstration. If I take this mass and just give it a little force, what's it do?
It moves.
It moves. Is it still moving?
No.
What's its natural tendency to do?
Stop.
Everything do that?
Yes.
Yes. Yeah, everything has to stop.
Even a trolley?
Eventually.
Eventually. What if you throw a ball?
Yes.
All right, what if you fire a bullet?
Yes.
What if you fire a rocket into space?
No.
Oh,
Floats.
it
Like
floats.
no gravitation to stop it or pull it down.
Once it gets away from Earth, does it stop?
Yes. No.
Robert says no.
Not until it hits something.
Not until it hits something.
Like planet.
Okay. If we can say that about rockets that we fire into space, then it wouldn't... And rockets are bodies, and in orbit, yeah. And rockets are bodies. This is a body. Then when we talk about the natural state, we're really talking about the natural state of motion, right? We're talking about the natural state of motion of bodies. And philosophers used to wonder, is it a natural state for things to come to rest, to be at rest, or to keep moving? From what we've talked about so far, what would your conclusion be? Do things tend to come to rest, keep moving, or something else that you might like to suggest? Ideas? Jody?
They tend to stop.
They tend to stop, like rockets that are going into space.
Well, except for that.
Except for that. But we want... Do we want to include everything? We want a statement that will include everything. And if rockets don't stop, if their natural tendency is not to stop, maybe the natural tendency of this mass is not to stop, nor of this trolley to stop eventually. Right. How do you stop it, Robert?
I put my hand there.
And by putting a hand there, you're applying what? A force. Okay. What tends to stop things?
Force and gravitational.
Forces. Gravitational forces, do you reckon? Okay, forces generally. All right. Okay, rocket moving in space. Is there any force acting on it if the rocket engines have stopped firing?
Yes.
Which-
Gravitational.
Let's say it's got well away from Earth and it's well away from stars. It's travelling through interstellar space. A long way.
No, it's not. No.
No forces?
No.
Any other opinions?
The force is breaking up.
June? You think it should have a force on it because it's still moving?
No.
Ah, that's good thinking. What do you reckon? If something's moving, it's got to have a force on it to keep it moving. What do you think about that?
Yeah.
Sounds reasonable, doesn't it? It all sounds feasible. That's what tricked people, you know, when they looked at things like this. Comes to rest, stops. Must be its natural state of motion, is to stop. That's its natural state. Everything should be at rest. Everything tends to come to rest eventually, sooner or later. Rockets don't. That's a problem. It's good, just as well the ancients didn't have rockets to contend with. It would have been a real fly in their theory, wouldn't it? Would have mucked up that theory. So now these days we've got to have a theory which explains why they were wrong, or why rockets do indeed keep moving after the engines are turned off. What do you reckon? Which way do we go? Do we try to explain why a rocket will keep moving when the engines are turned off? Or do we try to explain why the ancients got it wrong in saying that everything should come to rest? Let's look at the rocket situation. Who's in agreement on this, that things that are moving have got to have a force behind them to keep them moving? Who thinks that's right? Don't be shy. It's okay to think that. All right. Who disagrees? Oh, the heretics put their hands up. Oh, this is good. I like the heretics. Matthew, why do you disagree?
Because it just doesn't seem right.
Why? Tell us why.
I don't know. I just don't think it's right.
You got a gut feeling about this, have you? All right. Who else said they disagreed? Jay.
Because there's no, there's a force stopping it.
What force is stopping what?
So when you skid it,
Yeah.
it stops from friction.
Friction.
Like there's no friction or Or when you throw a ball, it falls down because of gravity. But in space, there's none of that, so it doesn't stop or fall.
Very good. Right. Okay. Now look at your sheets. You'll see where'd the spare ones get to? Up there. There we are. Thank you. You didn't notice that, did you, Robert? You weren't going to help me. Ever heard of Galileo?
Yeah. No.
Well, this is a little bit of a riddle to start with, and you should get it easy now. Galileo thought about it. Ever heard of Newton?
Yeah.
Good. Newton formalised it, which means that he wrote it down, made laws out of it. While we're all affected by it and experience it, even if we're not aware of it in scientific terms. What is it?
I don't have that sheet.
Oh, there you go. Pass that down to Anna, please. What is it?
Rebecca doesn't have a sheet.
Law of scientists.
Oh, Becky, how could we miss out two lovely ladies like you? There you go. Okay. What is it? Anyone got a clue yet? Yes. That's right. I said it'd be easy. Now let's read on and see what other clues I'd given. It caused people for hundreds of years to think that the natural state of motion is at rest because it makes moving things stop, just as Jay pointed out. Okay. Then there's another list. There's a list of things there about friction and some of its effects and some of its influences. All right. Put the sheet aside for a minute. Is friction important to us? If so, why? Where? I mean, anybody got a pen in the hand at the moment?
Yeah.
Got a good grip on it?
Yeah.
All right. You're sitting on a seat, aren't you? You got a grip on the seat? What if the seat was really slippery?
You need friction to stay.
You need
Friction.
to
Stay on.
stay on it. Right. Very good. What? Before we look at friction in our lives some more, what do you think friction is? It is firstly and foremostly what? Yep.
Forces and gravity.
Forces and gravity?
Forces?
Forces. Let's just say it's a force. How about that? All right. Are we all comfortable with it being a force?
Yeah.
Okay. Friction is a force. Now, let's just for a moment go back to the rocket and the majority of opinion here that things that are moving need a force to keep them going. Who's still comfortable with that? Want to still support that idea? We've talked about friction, we've talked about things stopping. Dana, you still comfortable with that? Good. Who else? It seems to be a lot less at the moment. What's the matter with you? Giving up so easy? Come on, a little bit of fight in there, eh?
But there's like evidence to say that it's not, like the rocket.
Say that again, go on.
Because like you can't, like, with the rocket, there's not like force pushing along the air up there.
Air up there. No air up there. Okay. But there's no force pushing it along. We agreed there was no force acting on the rocket, didn't we? Did we agree on that?
Yeah.
Anybody disagree?
No.
Dana again. You're a real fly in the ointment, aren't you? I like it. What?
Through like
Dana, if we're all saying there's no force acting on the rocket as it's travelling through empty space with nothing around it, what force do you think is acting on the rocket?
It needs something to make it go.
You still convinced it needs something to make it go?
I agree.
You agree with Dana? Who agrees with Dana? Good, okay. Who's changed their mind in the process? Anybody agreed at first and has changed their mind now? 1, 2, okay, 3, righto. Okay, we'll come back to that a little bit more later on because we need to talk about forces and things moving. Okay? Let's just look at this one more time. Does this take a force to get it moving?
Yes. Push.
Does it take a force to stop it moving?
Yes.
What force was that?
Friction.
Friction. Okay. Now, what if there was no friction?
It just slides.
It would keep going.
It just keep on going. Sliding.
Okay, Dana, would you agree that after I'd given that a force, a shove like that, and I'm not touching anymore, would you agree that I'm not applying any more force to it?
Kind of, yeah, but no, because
Yes and no.
because you friction that.
Yeah, but I'm just talking about, like,
You
it's
applied
sitting there.
force before, and like it loses the force gradually, slowly as it's sliding across the table as it gets slower.
Loses the force.
Yeah, like loses energy. Like you've given
Well,
it
energy is
force.
different from force, isn't it? We learnt that earlier on. Okay. All right. Is there any force being applied to this by me at the moment? No.
Yes.
Is there now?
Yes.
Right. I'll just give it a short burst of force. Once it left contact with my hand, are we agreed that I was no longer exerting a force on it?
Yes.
Okay. But would you agree that the force of friction stopped it?
Yes.
Okay. Was there any other force stopping it other than friction? Well, gravity, you say. Okay. Which direction does gravity act in?
Pull down.
Down. Which direction is it moving? To stop something moving that way, don't we need something acting that way rather than that way? See,
Air pressure.
air acts against it, right? Air resistance, we might say. Resistance to air, good. Okay. Anyway, coming back to this argument. After I've set it in motion, let's say there was no air resistance and no friction. Got that?
It just
No air resistance, no friction. Who says it'll keep moving? Any dissenters? Anyone disagree with that? Right. If it keeps moving, a number of you said it needs a force to be acting to keep it moving. What force is then acting on it to keep it in motion? Can you tell me that? I've stopped exerting that force on it. And we said that there was no air resistance and no friction, but that would tend to stop it rather than keep it moving. So what keeps it moving then? What force is keeping it moving, Dana? No, I've taken my hand away after that initial contact like that. It's no longer there. Craig?
today.
Stored energy, is that a force?
Yes.
No, we're talking about two, like apples and oranges, all right? Can't talk about them as being the same. Add one apple and one orange, you don't get two of something. You get one apple and one orange. So force and energy, different ideas. Okay. All right. We'll talk more about that at the end. Okay. What I want us to do now is to consider the question of what is friction and what determines how big it is. Does it matter how big the force of friction is? Are there circumstances where we need friction to be maximised and other circumstances where we need friction to be minimised? Give me some examples by putting our hand up and not calling out all the time. Give me some examples of where we need to maximise friction. Alex?
In a racing car, like the wheels have to have more friction so it can handle the corners better.
Traction, right? When turning a corner, you need friction between the wheels and road. Very good. All right, Jody?
You also need it on a car when you want to stop,
Brakes?
to brake.
Yep, certainly you want a lot of friction there to stop. Yep.
If you have too much, it wears the motor.
But if you have too much, it wears the motor. So we want less friction inside the workings of the motor and more friction between the tyres and the road in cornering, all right? But not while we're travelling along. What about yourself and personal effects and things like that? If there, well, let's ask the question about your clothes. How do your clothes stay on you? Oh, I can see what you're thinking. Dana? They're what?
Really tight.
Really tight. Okay, if things are really tight, they tend to have friction. Okay? If you hold something, just borrow that pen from that. Now I want you to pull it out of my hand. Okay, easy? Was I holding that very tightly?
No, you need more friction.
I need more friction. Let's give it some more friction. I've got some more friction. Pull now. Bit harder now, isn't it?
Hands.
You didn't have enough friction. You got slippy hands.
Yep.
Right? What tends to decrease friction?
Water. It's
Water.
slippery like.
What's a word that's more general than water? Moisture, liquid. L starts with L. In cars. Lubricants. Very good. All right. Okay. Sometimes we need to maximise friction. Sometimes we need to minimise it. Now, what determines how big friction is? How large it is? Yasmin? Newton. Newton said it was going to be a certain size and it's going to be a certain size. We're really talking about, like Newton discovers laws and ideas, he doesn't make them up, okay? Newton discovered gravity, he didn't say how big it would be, so I don't think Newton got that big a say in the role of the universe. Jay?
Its surroundings, like where it is.
We need to be a bit more specific. We'll come back to you. John?
What sort of surface?
What sort of surface? What if this was ice here? Would this go more easily?
Yes.
All right. If it was sandpaper,
No.
wouldn't slide so easily. So the nature of the surface is important, yes?
Yes.
Right.
Wet and slide.
Now, what else makes a difference? See if you can guess
Flat.
as I start to do this.
The flat hard surface.
We've talked about the nature of the surfaces. Something else. Something else determines the size of the force of friction. John? Luke?
Is it the ability of what the thing weighs
weight.
already?
What it weighs. All right. Why would the weight make a difference? Look, I can demonstrate that here. If I give this a little push, it just rolls along like so. If I put some weight on there and give the same little push, it doesn't go quite as far. And the more weight I put on there, the more force I'm going to exert to get it going, isn't it? And what's more, it will
It's only like a flat
Flat surface.
go fast down the hill, yes, but with more weight on here, do you think it's going to stop this from going so far?
No.
No?
No.
All right. Because it's...
It's gravitational pull, and if you'd say if you push like it harder, it'd be the same as pushing it softer because it's got weights on.
All right.
Still got the same.
Let's ask a different question. Let's say we had a flat board here and you had a rope attached. You're going to drag your mate along on that like a sled. And you had one person on there, you drag them along, not too bad. That's easy enough. And then your friends turn up and they all jump on. Is that harder?
Yes.
Why?
Because it's way too much.
What have all those extra masses done to the force of friction? Increased it. Okay. They're the ideas that we're going to test. Turn to your sheets now. You see number one, how do we measure it? What is it again? Friction. Good. There's some instructions there. Then over the page there's some tables for you to record your measurements. And number two, what determines how big it is? And then we go on to effects of surface area. And then at the end, we've got a couple of interesting questions. Does it exist in a vacuum? Does it exist without gravity? We'll talk about those later. First of all, we want to accumulate and gather data that supports our suspicions that friction is determined by, that is the size of friction, how much friction there is determined by the force of gravity on the body that's moving, and secondly, the nature of the surface. What about the size of the surface, the area? If we take a block like this and we want to move it along like so, then we want to move it along like so. Would it be easier one way or the other way?
It would be easier that way.
Well, the grain.
Easier on the smaller surface?
Surface
Okay, well you're going to take measurements to test that. All right? You've got your predictions, you've got your ideas now, and you're going to find that out. This one might be the more interesting one of them all. Now, bear in mind, you're going to be using spring balances, and what did I tell you about spring balances yesterday?
Always accurate.
They're not perfect. And so when you take measurements with them, we've got to see that a number of measurements that vary by 10 or 20 grams, when we're measuring 500 or so, can mean that the measurements are the same. We've got to bear that in mind when we draw conclusions from our results. Okay. Your needs for this activity are going to involve a block of wood. Thanks, Ollie. These are friction blocks, and you can see that that's for checking out the nature of the surface. That comes later in the instructions. So don't take those first. You've got spring balances here. The blocks. We've got scissors. Well, there's a heap of scissors there, and there's, in case you all thieve those, these are tied on. Or, yeah, okay, you could cut them, couldn't you? But you're honest people, so you're going to need to take a section of string from here to attach to your block. And these are weights for when you come to the section that deals with adding weights. But the first bit, have you read the instructions for the first bit yet? What are you going to do with the first bit? Someone tell me. What are you going to do? Yes, Ollie?
No.
Someone who's read it? What are you going to do with the first? What's the first one, Jay?
With the spring balance, takes to pull along the block.
Okay. There's two parts to the first one. The first one is how much force does it take to get it started, and the other is how much force does it take to keep it moving. Do you think it's going to be different?
Yes.
Yes. Oh, why? You don't think it's going to be different? Who thinks it's going to be... Look, to get a block moving, let's say I was applying a force. I've got a spring balance attached to here, string, and I just stretch gently, slowly, stretch until all of a sudden, boom, it starts to move. And the force that I read, the maximum force in grams on the spring balance is the force that it took to get that moving. But if I start it moving, and then I just measure it as I move it along at a constant speed, and I read the force on the spring balance, is that going to be different from the one that I read to start with to get it moving? Oh, we have a difference of opinion. There's some yes, some no. That's good. We're going to find that out too. Okay? We're going to do 5 trials for each of these measurements. Why? Why do we do a number of trials, Jude?
To get the average, to get the closest to the...
That's right, because there's always errors associated with each of our measurements. By taking a number, we're more likely to get closer to the truth. Okay, when you think you know what you're doing, you move into your groups, come and get your apparatus, and begin taking your measurements. Hey? Yes, you can, yeah. Yeah. We didn't have any eye hooks, so there you go, like that.
You're making the size look boring in Australia. You're making size look boring.
Thank you. You can tell me later.
No, I just want to say something because people
Good.
think like
Would you like
really boring and
to? Would
stuff.
you like to do the experiment?
Yeah.
Well, let's go and do it.
Yeah. I was just
We can
saying,
talk
I don't
about that
really
later. All right?
I'm trying to be so careful.
You can do this later.
I'm just saying because you make it look boring, make it look like you have fun and then at the same time.
Well, why don't you
Because
go
we
and
do.
have fun?
No, but we always have fun and you make it look boring. Make it look fun like you normally do.
We'll get there.
Oh, yeah.
You go and enjoy. Hey, Anna. Do you think that's appropriate behaviour in here?
No.
Well, you'll get sent outside if you do that. Let's get on with our work. Got your gear?
No.
What are you waiting for?
Pulling the string.
Oh, so you're getting the string.
Yes.
You read the instructions?
Yes.
Know what to do? Good. Now, one thing you've got to consider is the section of bench you're going to work on. You want it to be almost all the same. Okay? So clear things away a bit.
Do we finish all this?
Okay?
Do we finish all this today?
Oh, we may not finish all that today. No, we've taken a bit more time. No? Okay, you got your string? Start. How you guys going?
Fine. Go through it again. Just like on 50.
Alright. Now that's just getting it starting, is it?
Yeah.
Okay. You slowly stretch it until it starts to move. Now you're getting very small readings. Why don't you get one of the more sensitive balances? Because this is for bigger, when you've got bigger forces to deal with. Okay? How you guys going? Relax. You're on.
So how do you do this?
Now, choose a section of your bench here. It's all fairly smooth.
Yeah, there. Yeah.
Got any particles on there, move it away.
Are we supposed to get this?
Now, this spring balance, it's going to be a very small measurement, okay? There are more sensitive ones up there.
Yeah, but they're like stretched and broken. Yeah, we're like not working anymore.
No, you haven't had a look at them. These are good ones.
Okay, good.
Alright? Go and get one that's a bit more sensitive because we want a bigger measurement. Alright? Bigger reading. That's good. And then you just stretch it slowly until it starts to move, and you've got to watch carefully to see what the maximum force was.
Yeah.
Who's recording?
Me.
Yes, Oliver.
We're going to get someone else.
You know what?
These stools. Yeah, because the other time the other cat didn't get one.
Oh,
Yeah.
we'll talk about this furniture later, alright?
No, because in tutor we had new stools.
There's a special story with that I'll have to tell you later.
Well, okay. Now, please.
Oh, you're special, yes.
Yeah, because we got to sit on them today. Yeah. Yeah, but no, we're special.
I'll see what I can do for you with the stools, alright? Yeah, right. Yes, girls. You've got the wrong block to start with. You want one of the ordinary plain blocks to start with. This is a friction block. Okay? Did you remember the one that I... just up in the box up there? In the tray? There one left there? Yep, there they are. Just over there. Yep, anyone will do. Anyone. Okay. Know what to do?
No.
Well, have you read?
Yes.
You do? Alright. Now you've got to tie that on there, but do that when I finish talking.
Okay.
And then tie the other end on here. Now you're going to just slowly pull on this, keeping it flat. Pull on it until the block suddenly lurches forward. And then where that gets to, read it off on the grams side here. That's going to be your maximum force to get it started. And you record it in your table over here. That's number one trial. Then you do it again for a number two trial. And you start from the same place each time. Okay? And then you repeat it, but this time, for this one, you get it moving first and you read its measurement. Okay? Good. How you going, boys?
Pretty good. We
Got some measurements?
yeah.
Now, wait. What are you writing it there for?
Because it says record your results here below.
Yeah. See, I draw a nice table for you, and you want to write over there.
You know which one's different like that.
Well, you just keep it on one surface first, right? And you record in that table. You're doing 5 trials.
Okay, I'll do the next trial too.
Now, this spring balance is a big one. Why don't you get one that's more sensitive to these measurements, because it won't go far on the scale there. This is for when we put the weights on it.
Okay.
All right?
Yeah, I'll read it.
Where's your group, Jay? Here?
Yep.
You got any results yet?
Yep.
Why are you using this spring balance rather than a more sensitive one? This is for when we put weights on there. This is when you need bigger forces.
Alright, I'll go bigger, smaller.
Smaller one be good, yep. be a bit more sensitive to it.
Oh, no.
50, 50, 100. What's happened here?
200.
Was it all that different?
175. 175. No, I saw 200 when exactly.
Ah, guys. You've got the spring balance that measures the bigger forces. This is when we put weights on here. Why don't you get the little spring balance that's more sensitive?
Oh.
Yeah, think about those things, all right? Rob, why don't you point that out to the guys? You didn't think about that, did you?
No. Alright then.
All right. Okay, you rebels. Troublemakers down here. Hey. Why have you got this spring balance? Why don't you get a more sensitive one? Because look, it's not reading very much. See? Get the spring balance, it just reads up to 100. Alright? You've taken one measurement already, have you? 50. Do you understand why I'm saying that about the spring balance?
Why'd you put it out for?
Because when we add weights later on, we'll need ones which are bigger readings. They're in separate piles, and I wanted you to think about it. I wanted you to figure that out. Yeah. I got you on that one, didn't I? Is that 100 grams? That's it. Use that one.
When to work, right? Do we...
No. Maybe I didn't tell you guys. You want a more sensitive spring balance for this one. These read to a kilogram, all right? And you're only going to pull down to about there, all right? And there's a lot more error in here, okay? This comes later when we put weights on it, okay? So whip up and get the little balance. 100 grams, even a 500 would be all right. Now, what are we going to ask anyway?
When you do it, when you pull it, and it goes to a high point, and then it goes back to a low point. Do you do the higher point or the low?
The higher point, because it's what's needed to just get it started. Okay. Now, if you use that one, it's going to be more sensitive. Okay. Now, these are in newtons. Now, to convert them to grams, we just multiply by 100. So that'll be 50 grams, 100 grams, 150, 200. This goes up to 250 grams.
Oh, okay.
All right. So it's just a confusing one, isn't it? Oh, did you read it?
That was right there.
Got up to there, did it? See, I wasn't looking. Let's try that again. Let's try it again. You yell when it starts to move. I'll do this very slowly. Oh, got up to about there, didn't it? All right. What do you reckon that reading is? That's 1.4? 140. Very good. That's what you'd record. Then you push it back and do it again.
You said it would only be something like 80 or 70 grams.
Oh, I was a guessing.
This one read similar. So yeah, it read similar.
Well, that means it's a good balance. But we can't be guaranteed of that. And errors in here. See, if you make an error of 10 in 100, what percentage is that? 10%. Okay? But the errors involved, you know, the spring in here is just as stiff as the spring in there. So while this moves a distance here, it makes a bigger reading. There's a bigger amount of grams in the same distance move there than there is in there, isn't there? So that's why this one's got bigger percentage error. You'll learn more about percentage error as you go on in science. Well, ladies, how are we going? Very good. That means you've got some very consistent results, and by golly, look at those results. That's brilliant. That's brilliant. Excellent. Who was reading that? Phyllis. Well, you guys are going to be scientific experimenters, huh? Look at that. Beautiful. And hey, look, these are generally looking a bit higher, are they?
Yeah, a bit
Better than those.
Yeah.
And this was the one when it was already moving. You're reading that.
It went up and then it went down. We couldn't know if it's supposed to write down.
I'll show you.
went up and it went down.
It's better to see it happen. And we'll see if you've done it the way I mean you to do it. Just move this away a bit. Now, you get it moving and you read it while it's moving. What's that reading?
100.
About 100. You've got 120 or something there, haven't you?
Yeah.
Let's do it again.
I didn't read that one. That was Olivia.
What's it?
120. Haha.
Now, no, down there.
Alright, I can't read it. I'm not sure. So that's 80.
About 80.
Is that 90?
No.
You got to keep it moving at the same.
They're like 30 or 20 off, and you said that.
Yeah, we'll worry about those when we look at the averages. All right. So look at this. I'm getting an 80 reading again. You've got 120. You were reading this.
The first one was Olivia. The rest were me.
Oh right. Okay. Would you like
Not Sasha.
to try those again? You reckon you might like to try them again? Just check it out. Okay. And remember, you've got to get it moving first, and you've got to keep it moving at a constant rate, and then read what it says. Got it? Good on you. Okay. How's the results going, guys? All right. And this one's less.
Yeah.
I'm proud of you guys. You're supporting the theory. Love it. Is that what you would have thought?
No.
You would have thought it was the other way around?
Yeah.
What would you, Alex? Well, I want to hear why later on. Okay?
When I was constant,
What have we got?
24.
Oh, this is starting to look lower. You reckon it should be lower?
Really?
You reckon it should be higher? The same?
I think it should be the same.
Same. Why do you think so?
Because like when you tug it, you use more to move it, and then when it starts moving, you use less.
Why do you use less, Bart? This is not an easy question to answer, I might add, so I'm interested in why you think that. Okay, we'll talk about it later. Yeah, this is something for you to worry about now, all right? But don't worry too much, all right? Get your results down first, because all science is based on your results, all right? Data. You take measurements and then you draw conclusions. Okay, keep going. Come on, guys, how are we going? Let's have a look at your results. 110, 150, 160. Oh, you're all over the place, aren't you?
Yeah. I reckon the quicker you go, the more.
Yeah, but this one's just for getting it started, isn't it?
Yeah.
All right.
Except the quicker you go, like.
But what do you mean the quicker you go? What? No. Did you not hear me say that you should hop off there a minute? You should do it like this. You just slowly, gently increase until it moves. All right? Slowly, gently, and then when it moves, boom, that's what the reading is. Okay? And some of yours are pretty high, aren't they?
Yeah.
Maybe you'd better do that again now you know what to do. Good. You guys hear that? Listen to that? Yeah, but you're the mathematician, all right? You got to get the results right first. you got to go for the technique first, all right? Ask Luke what I've just shown him. Let's see how my favourite ladies are going now.
I see that louder, so we can hear.
50 what's this 0.2 here? 0.2?
That is like 20 grams. That's 20 grams. That's how
Okay,
it's
well,
read.
write it all as grams. Write it all as grams, okay? You got 50, 20, 40, 50, 50. All right? Okay. See how you go with this one. Now, you know what you've got to do with this one, right? I'll show you. You've got to get it moving first. Hop up. Becky, hop up. Hop out of the way a bit. Okay. Now you get it moving, and then while it's moving, oh, this is a bit jerky here. Get it moving, and there. Now see the reading there? That's what we want.
See it first.
Well, you saw what I was doing, right, didn't you?
That's my eyebrows.
Yeah, I know. All right. You got the idea?
Becca's not watching.
Who's going to do this?
Me.
Who's going? You are. Good. Right. Then you see what I'm doing?
So it's
See what I'm doing?
Yep.
Point.
0.6.
It keeps on moving. You've got to move that.
You've got to keep it going at a
Same
constant speed.
Yeah,
Yep.
you're going.
Yeah. Okay.
Well, what do you see? What happens is that the surface changes a bit from there to there, and so you want to make sure you get it on a section of surface that's fairly uniform. All right.
All right.
Get me some results.
Get me some results.
Get yourself some results. You what?
Do number 2.
Yes. You keep moving on.
Where did we get the weights from?
Oh, up there in the tray. You saw the ones I put on the trolley? There's a whole tray of them up there. Let me have a look and see what you've got here. 8, 10. Oh, these are quite low. Okay, but they're smaller than those, right? Should that be so? Should be, should it? You really feel convinced about that? Well, we'll talk about why later, okay? These are quite high compared to these. You sure you did those right? Read the scale right? Okay, all right. You're ready to try adding weights to your block? Okay. Those weights up, and add each of those weights that I showed you, they're 500 grams. Add 500 grams at a time and work up for each of their trials. All right? And the force here is in grams, so it's 500, then a kilogram, then 1.5, and so on. Okay. You've got to stack them on top of that. You might need that bigger spring balance, the one you had earlier on, to replace that once the force gets too large and this goes off the scale. The 1 kilogram one, yep.
Okay, is this answer enough?
Because one is constant. We're going to talk about that. All right, you can have a bit of a guess at it now, but don't try to answer those just yet. Concentrate on getting our data down. Okay. 130. Oh, very well done, girls. That looks good. Okay. You don't know why it looks good, do you?
Because it's right.
Yeah, that's all right. You don't have to know why it looks good at the moment. It's just very pleasing to my eye. Would you have predicted that these readings should be smaller than those? You would have thought, what, the same? So nice to get a surprise once in a while, isn't it? Science is like that, full of surprises. That's what keeps people interested. Carry on.
We need some blocks now.
Yep.
How many weights do we use?
Well, you've got 5 trials. You just keep stacking on weights. Each trial is a different weight. And you can see why we need that one for this one now, don't we? Alright, okay.
Just to get it started, or
Well, what's it say? Try adding weights to the log and repeat part C. What was part C? Constant motion.
So we're getting like complete different results.
Oh, yeah.
We got 125 and 225.
125 and 225. Now it's 100. Is this surface different from yours, do you think?
It's rough there.
It could be a bit different, couldn't it?
Yeah.
You remember me saying that you should always... You've got to first of all make sure you've got fairly smooth surface so you don't have jerky motion. And secondly, when you repeat your trials, you do it over the same section of bench. Alright? So are you doing it over the same section of bench?
Probably not.
Right. Try that. You'll get more consistent results. Okay? Well, guys, let's have a look and see what you've got here. 150. Right, these are smaller than those.
Yeah.
What's the meaning of this?
Yeah, it
Why?
takes more force to get it going.
Why do you think that would be? Did you expect that?
Yeah.
You did? Ah, why? Bit of a gut feeling or what?
It takes like more force to get something going than to keep it moving.
What's told you that from your previous experience? Something has told you that, hasn't it?
Yeah.
All right, you can't remember what? All right, think about it a little bit. I'd be interested to know where you got that idea from. Okay. Craig, did you expect that? You did expect that? All right, okay, that's good.
For the rest of the year now.
You what?
Can I sit here for the rest of the year?
Oh, we might be able to swing a deal on that later on. Yeah? What do you got to offer?
$2.70.
Increased effort?
I don't know.
My effort can never be increased.
Better results?
Yeah, okay.
Okay, that sounds like a good deal to me. How are results going here? 80, 90, 100. These look to be very similar to those. Would you agree?
Yes.
Okay.
Yes, but these, because you just need to have a greater force to get it to start moving.
Yeah.
But this is not saying that. This is saying that you need the same force to get it moving as to keep it moving.
So that's 88 grams. That's 92.
88 to 92, do you think that's a significant difference?
Faces not really.
Ah, I'd say they're virtually the same because of the inaccuracies in our spring balance. All right? That's all right. You're allowed to get those results. If they're the results you got, righto. You will be interested perhaps to know that a number of other groups are getting quite a bit of difference between these two. All right? But we'll talk about that later on at the conclusion of taking our measurements.
Watch it when it moves, you guys.
Have we ground to a halt here, boys, or what?
No, we've done like 2 pages already, or 1 page.
Yes, well, you've still got some to go, haven't you? What are you up to now?
We'll make one real
No, worry about that later. Go on to the next one here. Try different surface areas, okay? Those other questions I've inserted there we'll discuss.
Do we need another block?
No, what did I say you could do with that one? Oh, yes, okay.
You got that?
Yes, yeah, but if you're going to do it like that, you're going to have to wrap a piece of cord around there, aren't you, and link it up there. Get some more strength.
Well, we only got 3 trials, so we can do that, that, and that.
Okay,
Yeah.
that's all you'll need to do. Yep.
Aaron has got too much weight.
You've got to get it moving and keep it moving, don't you? It's like part C. No. Can I suggest that you're being a bit awkward with that? What you need to do to make it steadier, move it back to where you started it from. Thank you. Now, if you can just grab it like that and just quickly get it moving, and you want to keep it moving like that. All right, we're running across some uneven surface there by the looks of it. Take it right back. Okay. It's going to be a bit more awkward and difficult with those hips. But see how I'm holding it like this? So as you can get it moving quickly and keep it moving, but it's a bit difficult, isn't it? All right, take it back again. You need a little bit of practice. Okay, fast. There you go. See how you can do it?
550.
Well, you're taking advantage of my measurement, aren't you? All right, whip it back. You have to be quicker on this. Okay, you have a go at that.
No.
Yes, hurry up. What have we got up to, girls? Huh? Well, you better tell me your results quickly.
We just did that number C.
Part C. 0.6, okay, that's 60 grams, isn't it? 50 grams, 60 grams, 50, 20, 40. These are bigger than those. Interesting. You sure about that?
Yeah.
Who's taking the measurements? Who's doing the...
Me and Yasmin.
Okay, all right. Keep going. Yes, girls.
What do we do?
This one, you're using that block, and it's to do with surface area. Remember I said you could do it like that, you could do it like that, and then there's another one like that.
Do we need these on it?
No. Okay. And you only able to do 3 trials. That's 5 trials for each surface. But That's why we've got 3 tables there. 3 surfaces. Okay.
When we pulled it that way with the weights and when we pulled it that way, 2 different. Like when we pulled it that way, the recordings were higher.
Yeah.
But when we pulled it that way, they were lower.
Good. Right. Why do you think?
Different surfaces.
Well, the two same surfaces you were dealing with. What you've touched on is very important for understanding friction. Can I just have that block a bit? This is just one clue. If you run your fingers over that way, and then that way, does it feel the same? The same. No. And you were talking about pulling it in different directions, weren't you? What about the... Is it rougher that way? Or that way? That way, you reckon? Yeah. All right. And if it's rougher, why would wood be rougher in one direction than the other? Just because of the grain and the way it's cut. Okay. So, if it's rougher in one direction, that's going to make the frictional force, the size of it, directional, isn't it? You've picked up something very important. Very good observation. You're doing physics in upper school, aren't you? We want you.
The car getting bogged on the beach because there's too much weight.
Yes, good. But look, don't spend too much time on those. In fact, get onto that one. We want to do the measurements. We've only got a couple minutes left. Okay. 3 minutes by you, is it? It's 5 minutes by me. Are you right?
Of course I'm right. I'm always right.
Okay, we better call it all in now, I think. All right, folks. Stop, please. Thank you. Stop now. Now, I know that no one has finished, and that's fine because it's a long activity and we still have yet to conclude. We'll have to do that tomorrow. So what I need you to do now is to return all your gear neatly and quickly to the front and then resume your seats. If we've got a few minutes left, we'll talk some more. Yeah, we'll keep the string, thank you. You got onto the friction block, did you? Oh, you didn't. All right. Oh, Lukey. You're a worry, Lukey. Matthew. Okay, let's listen in for a minute. Now we've got just a few minutes left before lunch. I'd like you to, from what you remember from your results, the first one where you were measuring the force to get it started, get the block started as opposed to keep it moving. Who found that there was a larger force required to get it started than to keep it moving? Hands up, please. Right. Okay. Thank you. Who, put your hands up if it was significantly larger, that is 10 grams or more, 10, 20 grams more. Good, thank you. Righto, that makes it more reliable. Okay. Who got to doing the different surface areas? One group. Alex, okay. Andrew, what do you tell us what you've found so far in those measurements? Yeah, but are they? Is the force required to drag it along at a constant speed on one surface area significantly different?
It's different, but it's about 10 grams.
Oh, so it might not be that different. Okay. So you're not convinced one way or the other yet. All right. Okay. What about adding weights? Who found that adding weights meant it took a lot more force to keep it moving? Okay. Who was surprised by that? No one. I hope not. You were? Okay. Let's just consider. So you can pick it up. I'll leave you one question which we'll need to discuss next time when we're rounding all this off, and that is, how would you define the force of friction? How would you actually make a statement that says what it is? Okay? Okay, lunchtime, folks.